Good evening, everyone. First of all, I would like to express my gratitude to the conference organization for the invitation. My name is Slimane Debbaghi. I am associate professor in the University of Hadrawi from Algeria, and today I will present effects of fiber orientation on first play failure in symmetric composite laminates using the boundary element method and psi criteria. This study investigates how fiber orientation affects the onset of first play failure in symmetric laminated plate with a central hole under in-plane loading. We employ an isotropic kernel boundary element method to stress recovery and predict FPF using psi-heal and psi-u criteria. The results show that the optimum angle improve strength and delay failure. Composite laminate widely used in the automotive and aerospace. However, due to the high strength to weight ratio and design flexibility. However, the presence of hole and cutouts cause stress concentration and early failure may be appear. First play failure is a conservative and practical design target. Most phased failure maps rely on CLT classical lamination theory and the finite element method. Classical laminate theory alone is insufficient. It ignores local stress concentration. Boundary elements offer boundary-only discretization and accuracy near stress gradients. The objective is to analyze symmetric laminates with off-axis play and assess first play failure using psi-heal and psi-u criteria. Our workflow began with material property, stacking sequences definition, CLT analysis, anisotropic kernel boundary element method to stress recovery near hole, and finally we find the first the failure in this of criteria of psi-heal and psi-u criteria. The classical laminate theory here briefly explained, formed by reduced stiffness matrix from the property, material property, the transformation to the play angle, and the laminate matrix A of stiffness equal to the contribution of all the play multiplying by the thickness. The mid-plane strain is computed from the matrix of stiffness and the load. The play stress transfer from the global coordinate to the local coordinate of play. Orthotropic for orthotropic compliance plane stress, the laminate the fiber is considered as an orthotropic laminate. The matrix of stiffness is composed from the element of property of material and the coupling or the term of coupling. The off-axis play at angle theta must be transformed to the the matrix element. The matrix must be transformed to the fiber orientation. Leknitsky characteristic equation, quartic equation, good give us the roots, the four roots, which is define some complex to determine the fundamental kernels. We have here the displacement kernels and the traction kernels. Discretization of our model is about it is a square hole, a plate hole with a central circular hole in plane traction, and the element trained quadratic on both outer edge and hole. The unknown relay by this equation of boundary integral equation, the stress recovery near the holes from and then transform to play axis. FPF computes the failure index of psi-heal and psi-u criteria. The Tsai-Hill and Tsai-Yu criteria suggest the failure 1F is greater than 1. And Tsai-Yu is often more conservative than Tsai-Hill because Tsai-Hill is simpler than Tsai-Yu. Our contribution in this work is the combination of the boundary element method with the CLT analysis to perform the Tsai-Hill and Tsai-Yu index of failure. Here we have the stress boundary element method near computed by the boundary element method near the hole and corrected by the stress concentration factor. The model set up by generating 18 quadratic elements holes and 30 element side per side. The number of integration points is 3. Loading remote tension is 100 MPa, and the orthotropic play volume. The validation of the code is compared with the Kirsch model. Here we have the hoop stress near the hole, and this slide shows the variation of the maximum index of failure with the angle, with the variation of angle. Here we have a safe condition around under 45 degree, and unsafe condition above 45 degree. The application of boundary element method to compute the stress near the hole give us this slope, which we can see here clearly that the stress near the edge of hole is considerably big. But the CLT analysis give us a safe condition, which is wrong in the hole in the edge of hole. Here we have a stake of the first one. This is a stake of 45 plus minus 45. And here we have a stake of plus minus 30. And we have a stake of plus minus 60. The same, we can say here clearly that the CLT give us unsafe situation. Unsafe situation because the failure index is above 1. Our techniques utilize compute the failure index respect to the angle for the stake of plus minus 45, and we have here, and we say here a drop of the maximum of the failure index under 1.5. Here we have the same geometry with the stake of plus minus 30, and we can see here that the laminate is safe because it's under 1 index of failure. Here we have a stake of plus minus 60, and we can see here that a big zone of unsafe situation for the because of the orientation of the fiber. Here we can revalidate our code with the variation of index of failure, maximum failure criteria along the angle. Here we have this table summarize our result. The CLT baseline give us safe situation for this stack plus minus 30. The boundary element method give us a peak of 17 and 30 because it's take on consideration the gradient of stress. And here our techniques is to combine CLT with the boundary element method to compute the failure index, and we have a safe situation. Here we have for the stack plus minus 45. The CLT give us a safe situation, but the boundary element method give us unsafe situation. Our techniques give us unsafe situation. For the plus minus 60, the CLT give us unsafe situation with the other techniques. Here we can get the allowable loading, and we can see here for the whole laminate, and we can see here that the good structure is around 45 degrees. In our discussion, the fiber orientation strongly influence first play failure and allowable load. SIU is not always more conservative locally, and boundary evaluation around the hood is sufficient for critical metrics. Boundary element method plus CLT plus TSI criteria provide efficient first play failure prediction for symmetric laminates, optimum fiber angle delay first play failure, and increase margin. Consider both SIU and SIU to brackets design. Our reference, and thank you for your attention.